So maybe it's easier if I draw the picture. So let me try to draw 3 mutually tangent circles. So maybe I'll draw like this. 1, 2, 3 like this. And it says that there are exactly 2 circles which are tangent to all 3 of them. So where should these 2 circles be? So maybe we can try to draw one here, and then maybe another one, because it has to be tangent to 3 of them. So it's not so clear actually if you can draw tangent circles, this larger circle which are tangent to the 3 of these circles. So okay, so it's not so successful, this picture. Okay, but it's a theorem. So but how do you prove this? So I'll give you a proof. So the proof uses Möbius transformations. It's an action of SL2C on the extended complex plane. So take 2 by 2 matrices, 2 by 2 matrix in SL2C, which means that so A, B, C, they are complex numbers, and determinant is 1, and it acts on C hat. So it acts on C hat. So C hat means the extended complex plane. So we just add the point at infinity to the complex plane C, and the action is just the linear fractional transformation. So A, B, C, D, Z goes to AZ plus B, CZ plus D. I'm sure you've seen this Möbius transformation in complex analysis course, yeah? And one of the actually basic property of this Möbius transformation action is that it maps circles to circles. Okay. But when I say this, I have to clarify one thing. So when I say circle, so I'm going to include a line. Okay. So because the circle which passes through the infinity will be just lines. Okay. So lines, including lines. So in the extended complex plane, the circles include the lines, the usual Euclidean lines. And then when you allow these lines to be included in circles, then it's an exercise that any 2 by 2 matrices with determinant 1 would move circle to circle. It does not preserve a center, but anyway, the image of circle will be a circle. And it also preserves angles, preserving angles between them. So for instance, if you have 2 tangent circles, then the image will be again 2 tangent circles because it has to preserve angles. Okay, so we'll use this property of Möbius transformations to prove this. So we started with these 3 mutually tangent circles, and take any point, any tangent point here. So let's call it P. Let's call this point P. So P is a tangent point, and we'll take a matrix A which moves P to infinity. Okay? And again, you should remember maybe from your complex analysis course, SL2C acts transitively on C hat. So I can do this. So take a matrix, say A, B, C, D, A from SL2C, which maps this point P to infinity. Okay. So now let's try to think what should be the image of these 3 mutually tangent circles. It has to be, so maybe I'll draw it here again. I have these 3 circles. And this is my point P. And A should move this P to infinity, which means that A should move these 2 tangent circles to lines, because now it has to pass infinity. And then these 2 tangent circles now should be 2 parallel lines, because it has to be tangent at infinity. So these 2 circles will be mapped to these 2 parallel lines. But now, what about the 3rd circle? This 3rd circle should not pass infinity, so it's not going to be a line, but it has to be tangent to these two circles. So it has to be exactly of this shape. Okay? But now in this shape, so it's easy to see why this theorem has to be true. So here we are given 3 mutually tangent circles, and where are 2 circles which are tangent to all the 3 of them? So these are this, yeah? We have no other choices. Okay, so here I prove Apollonian theorem, but now we go back using A inverse. Okay, now what are the image of these 2 yellow circles? The image of 2 yellow circles must be exactly this one and this one. Okay? Because these 2 yellow circles, it has to be tangent to the 3 of them. Okay? So we just proved that there exist exactly 2 circles which are tangent to these 3 of them. Okay? And so this theorem of Apollonius, so this is the basis for the construction of Apollonian circle packing. So now I explain Apollonian circle packing. So to construct Apollonian circle packing, we'll begin with the 4 mutually tangent circles. So the first step, so start with 4 mutually tangent circles. Okay, again by Apollonius, we know that we can draw 4 mutually tangent circles. You can draw 3 mutually tangent circles, and then there exists the 4th one. So here is a 4 possible configurations. So one configuration is what I just drew. So this is one possible configuration of 4 mutually tangent circles. Or instead of drawing this circle inside, I could have drawn this one. And another possibility is that I could draw like this, and then 4th one right here. And then another possibility is this. Okay, so here are 4 possible configurations of these 4 mutually tangent circles. 2. Add 4 more new circles. Add new circles which are tangent to 3 of them. Okay, so maybe I'll draw with this one. So okay, maybe I'll try to draw a bigger picture. Okay. Then, in fact, there are exactly 4 more new circles which are tangent to the 3 of them. Because if I choose these 3 circles, then I have already 1 circle which are tangent to 3 of them. So by Apollonius, there has to be only 1 more circle which are tangent to the 3 of them, which is this one. Yeah. Now, if I choose these 3 circles, then again, this one is already tangent to these 3 of them. So there has to be exactly 1 more circle which are tangent to 1, 2, 3 of these circles, which is this one. Okay? And again, the same goes for this one and this one. Okay? So this is 2nd generation of the packing. Now the 3rd generation, we just continue to do this same process. Continue to add newer circles tangent to 3 of the previous ones. Okay, so now I use the red chalk. So again, 1, 2, 3. So for these 3 of them, so we can draw this circle. This circle is tangent to these 2 white one and then this yellow one. Okay, so this one is tangent to 3 of the existing circles, so I can add this. And for each of the triangular region, because the triangular region has 3 sides consisting of 3 circles, tangent to 3 circles, I can add newer circle. Okay. It's supposed to be all the circles. Did I finish? Okay. And then we do it again. So again, we get more and more smaller triangular regions, and then for each of triangular region, we can add newer circle which are tangent to 3 of the previous ones. Yeah. Okay, so now for the rest of my talk, I'll just keep doing this. Okay, and then by doing this, we arrived at infinite circle packing, and this is exactly Apollonian packing. So we obtain an infinite circle packing called Apollonian circle packing. So as you see, actually, it's very easy to construct Apollonian packing. Yeah. So using this theorem of Apollonius. So the question I'm interested in is that, for instance, if you take this circle packing, then you see actually the circles must get smaller and smaller. I mean, in this picture, actually, all the circles actually happen to be inside this big circle, and then because of this area consideration, you cannot have bigger and bigger circles. As we continue on this process, the circles must get smaller and smaller. So therefore, if you look at this counting function, say number of circles of radius bigger than a given number, then there will be only finitely many such circles. Yeah, because the radius must get smaller and smaller. But instead of labeling the circles with the radius, I'm going to look at the inverse of the radius, the reciprocal of radius, because the radius goes to 0, and then it's easier to send something to infinity. So instead of radius, I'm going to look at the curvature of the circle. So the curvature of the circle, this is again, you probably learned it in calculus. The curvature of a Euclidean circle is precisely 1 over the radius of the circle. Okay? So then the counting question is this. So for given Apollonian packing P, for given we look at number of circles in P such that the curvature is less than T. In other words, the radius of circle is bigger than 1 over T. Okay? And then if this packing is bounded packing like that, then this number has to be finite. Okay? Because you cannot have infinitely many circles of the same radius. So let's call this NT of P. Okay? And the question I'm interested in is to understand what is the behavior of this counting function as T tends to infinity. Okay? Yeah, it does tend to infinity, but we want to know finer properties than that. And more generally, so if you look at the bounded Apollonian packing, then this is finite. But if you look at unbounded Apollonian packing, for instance, in this picture, so the packing, if you finish the packing, then it would be of this shape. Then you will have infinitely many circles of the same size. Then this function will be infinite, because there will be infinitely many circles of the same curvature, as you see from this picture. And so therefore, instead of looking this function, we can modify this function so that for any bounded region, E in complex planes, say, you can look at, so I'll denote NT, say EP. So this will be, again, circles in a given Apollonian packing, curvature less than T, but we are going to insist that the circle must meet this bounded region, non-empty. Okay? So what it means is that, so if you look at all the circles, then we'll have infinity for this. So I'll just fix some bounded region E. Okay? And then I'm going to count only circles in this bounded region. Then again, because of this area consideration, because this region has to be bounded, this counting function will be finite for any given T. Okay? So this will be finite. So then we can ask, what is the asymptotic? Asymptotic of NT, EP, as T tends to infinity. Okay? So obviously, I mean, one easy observation you can make is that this asymptotic will depend on this choice of E, right? If I, for instance, take E over here, then this set, I mean, this function will be 0 all the time. So the answer has to depend on actually where E is located in the plane. Okay? But more importantly, what will be the order of T? Is it going to be T squared or just T or log T? Like what will be the order of the growth of this counting function? Okay? So to explain the result, so some basic invariants of this packing are called residual set of packing. So definition, so residual set. So for given packing, the residual set of P will be simply the closure of the union of all the circles in P. So I take union of C from P, but take the closure. Okay. So of course, if you take C, I mean, this is just circle. We have countably many circles. But if you take a closure, then the residual set looks like a fractal-like set. It becomes a fractal-like set. Okay. And this is called the residual set, and then this is the same set as, for instance, you can. This is a complement in C of the union of all the open disks enclosed by C. Okay, so the union of all the open disks enclosed by C, C from P. So here the union of closure of all these circles is same to say you just scoop the open disks enclosed by circles in C, and then what is left will be the same as the residual set. And the dimension of this residual set is called the residual dimension. So the residual dimension P will be dimension of this residual set. Okay, so what dimension? Yeah, so I mean, so this is a union of countably many circles. So dimension has to be at least 1, right? Because the circle has dimension 1, and it is a subset of a plane, so it cannot exceed 2. Okay, it's something between 1 and 2, but then of course it's not 1 and it's not 2. And then to measure such dimension, such a fractal dimension, there's a notion of Hausdorff dimension. Okay? So Hausdorff dimension. And this Hausdorff dimension, this measures actually just finer properties than the usual dimension we learn in linear algebra. The dimension could be a rational number instead of integers. Okay? And so let's denote this by delta. And what is known about this delta is that, so it's an easy fact about delta, the residual dimension. So first of all, this delta does not depend on the choice of P. What I mean is that, see, there are infinitely many different Apollonian packings. Like it depends on like which 4 mutually tangent circles I start with. So I could have this packing, or I could have this packing, or I could have packing like this. Okay? But this delta, the residual dimension, is an invariant of Apollonian circle packing. It does not depend on the specific choice of packing. Why is that? Can somebody see this? It's because actually when we proved the Apollonian theorem in the very beginning, we in fact observed that any packing can be moved to this packing by Möbius transformation. Yeah? So you can start with any packing and just move one tangent point to infinity, then it will go to this one because we have to see 2 parallel lines. Okay? And then the Hausdorff dimension does not change under the Möbius transformations. So in fact, actually, it's just Hausdorff dimension of that packing between 2 parallel lines. Okay? So since any 2 Apollonian packings are equivalent or can be mapped to each other by a Möbius transformation. So what is the precise number of this delta? It is not known. We know there is some number between 1 and 2, but the best record actually toward the exact number has been obtained by McMullen, who computed this is approximately 1.30568, something like this. Okay. So here's the record. I think it's 98. So it's quite big. I mean, yeah, we took the closure of all the circles, but actually it's quite big than just union of circles, right? Because the dimension is 1.3 something. And Boyd, 81, he proved the following fact using elementary computation. So he didn't quite compute the asymptotic of this counting function, but he looked at the logarithmic function of this. So he looked at logarithm of this, and he showed that if you look at log of nt, say EP, divided by log of t, then this converges to this residual dimension of packing, delta. And of course here I have to say something about E, because for instance, if I take E over here, it should be 0, not delta, right? So under the assumption that if, say, E contains, let's say, any triangular region in P. So what I mean is that in any Apollonian packing, you see this lot of triangular region. So as long as E contains one of these triangular regions, then E will contain, of course, infinitely many circles in it. Yeah. So as long as E contains such a triangular region, then this goes to infinity, and its logarithmic rate is given by this delta. But this does not quite provide the asymptotic growth of this function. And maybe you can guess that. What can you guess about now this function, if you know such a result? Maybe it should be something like a t to the delta. Yeah? If this grows as like a t to the delta, then if you take a log, then it will be delta log t, and if you divide by log t, it will be delta, right? But not quite. You could have also t to the delta times log of t. Yeah? But then still, if you take a log, actually, the log t divided by log t will go to 0, so it also gives the delta. Okay? So it does not quite say, actually, what is a precise asymptotic. Maybe it's a t to the delta, or it's a log t to the beta, whatever. Yeah? So what you prove is that, in fact, there is no log term. So theorem. So some special case was proved by Kontrovich and myself, and also myself and Shah. But it proves that we construct an explicit Borel measure omega on complex plane. So we compute some positive measure on C such that this counting function is asymptotic to omega of E. So the size of this bounded region E with respect to this omega times t to the delta. Okay? So for any bounded region E whose boundary is an algebraic curve. Okay, so maybe I should not have erased this picture of packing. So let's imagine again. We have this picture. Okay, so first of all, so we prove this result for any bounded region whose boundary is an algebraic curve. So what does it mean? So I can take any bounded region E as long as its boundary is an algebraic curve. Yeah. So for instance, you can take any disk. Yeah. Okay. Or you can take, if you believe this is an algebraic curve, you can take this kind of set. But one obvious thing that such a measure should satisfy is that E should not have a support beyond this packing, yeah? Because if I take E to be outside of this packing, then it should be 0. So we can guess that the support of this measure has to be in residual set of P. And this is the case. Otherwise, I mean, you would not believe such a theorem. Measure omega. So this measure is in this complex plane, but with support in residual set of P. So the measure has a support in here means that if you take E outside of the residual set, then it gives a 0. But if the interior of this set contains something from the residual set, then it gives a positive measure. And this theorem was proved by Kontorovich and myself when P is a bounded packing, and then when you take E to be everything. But this final property was proved in a joint work with Shah. Okay, so next. So what did we do? So here we had Apollonian packing, but we labeled each circle by curvatures of this circle, and then we counted the number of circles with these labelings. Yeah, with this labeling less than t. And one natural question you might want to ask is that, so what kind of numbers arise as these curvatures of circles? Okay, I mean, is it random, or is there some rule, or like what kind of numbers arise as curvatures of Apollonian, curvatures of circles in Apollonian packing? And for instance, you can ask, is there a Apollonian packing where all the curvatures are integers? Yeah. And the answer is yes, otherwise I would not have asked you. Okay, so, and this goes back to theorem of Descartes. In 1643. Actually, in those days, he wrote this theorem in a letter to the Princess Elizabeth of Bohemia. So, and I realized actually this princess was she was very smart and she was very good at math. So she was communicating a lot of letters about math with Descartes, and Descartes wrote this formula in one of the letters to her. Okay? And this is a beautiful theorem. So for any quadruple of 4 real numbers, so I mean a quadruple A, B, C, D. So for any real number, quadruple of real numbers, this can arise as the curvatures of 4 mutually tangent circles. So a quadruple is the curvatures of 4 mutually tangent circles. If and only if it satisfies certain quadratic equation. So very simple quadratic equation. Okay. So for given quadruple ABCD, as long as it satisfies this quadratic equation, we can draw 4 mutually tangent circles exactly with these given curvatures. Okay? But here actually I need to caution you one thing. So for instance, in this packing, 2, 2, 3, I think. Oh, okay. Or maybe I'll say this. So for instance, if you look at -1, 2, 2, 3, And this will satisfy this quadratic equation. So let's check. So twice over 1 plus 4 plus 4 plus 9. And this is what? This is 18 and 36. Yeah? This is 36. And then here, minus 1, 2, 2, 3 square. So this is 6. So this is 36. So this quadruple, negative 1, 2, 2, 3 satisfies this quadratic equation, right? But then I didn't explain what this negative number means, because I just said the curvature is one of the radius, and the radius is supposed to be a positive number. Okay? So I have to tell you what this negative 1 means. When we label the circles, we need to label the circles so that they have compatible orientation. What does orientation mean? For a given circle, when you talk about orientation, we have to say which one is interior. Is this interior or outside this interior? And then for the outer circle, we want to orient all the circles so that they have a disjoint interior. So for this outer circle, I need to orient this outer circle in the opposite way from the 3 other circles so that the interior of the outer circle will be outside. Okay? And then that's where the negative 1 comes from. So this one, if you draw the unit circle, so the circle of radius 1, so this will be exactly circle of radius 1. Negative 1 simply indicates that we orient it in the other way. Okay? And then circle of radius 1/2, so the curvature is 2, and the circle of radius 1/2, and circle of radius 1/3. You can draw, in fact, this circle so that they are mutually tangent to each other. Okay? And one of the amazing corollary of this Descartes circle theorem is that if you start with 3 mutually tangent circles, for given 3 mutually tangent circles, with curvature, say ABC, the 2 circles. So we know again by Apollonian, so there are exactly 2 circles which are tangent to 3 of these circles. The 2 circles tangent to those 3 have curvatures, say D and D prime, satisfying the following linear equation. So twice of D plus D prime. Oh no, so I think D plus D prime has to be twice of A plus B plus C. So what it says is if you have 3 mutually tangent circles, and then let's suppose that these 3 circles have a curvature ABC, and then you have 2 circles which are tangent to 3 of them, and then if you curve the curvature of these 2 circles and D and D prime, then these 2 circles must satisfy the linear equation given by this. And proof is straightforward from this Descartes theorem, because ABCD as well as ABCD prime, they both satisfy that quadratic equation. Yeah? So you have 2 equations, 2 quadratic equations. If you subtract one from another, you get some cancellation, and you get exactly this linear equation. Yeah? It says that in particular, if A, B, C, D are all integers, if A, B, C, D are integers, then so is D prime. Yeah, because D prime has to be twice of A plus B plus C minus D. So if A, B, C, D are integers, then D prime has to be integer. And this observation was made by Soddy, corollary. So Soddy, actually he was a chemist who was a Nobel laureate, and he made this amazing observation that if the initial 4 circles, 4 mutually tangent circles in an Apollonian packing, Apollonian circle packing, are integral, then what? So if you start with 4 circles which have integral curvatures like this one, Then I draw new circle, and the curvature of this circle has to be integer as well, right? Because this will be A, B, C, D, and this will be D prime. So this has to be integer, and so is this one, because this will be what? A, B, C, and which one is the fourth one? So there will be D. And then this one will be again D prime for some pair of A, B, C, D. Okay? Because all the circles we construct in each generation has to be tangent to the three of the given ones, and then there is already another fourth one which is tangent to the three of those previous ones. So if you started with quadruple of integers, then all the circles must have integral curvature. It's not obvious at all, like from the very beginning, right? Why should there exist an Apollonian packing with all the curvatures integers? Okay? And such a packing is called integral packing, integral Apollonian packing. So such packing is called an integral Apollonian packing. And not only it exists, in fact, the Descartes' theorem says that there exists a lot of integral Apollonian packings, because whenever you have an integral solution to this Descartes' quadratic form, then you can draw four circles with these integral curvatures, then this will give you one integral Apollonian packing. So there are a lot of integral Apollonian packings. Okay? And so we have these labelings of integral Apollonian packing with a whole bunch of integers. So when you see integers, what should you ask about them? If you see integers, then you should ask about primes. So we'll ask, for a given integral Apollonian packing, are there infinitely many circles with prime curvatures? Okay, so for convenience, let me define a prime circle. So prime circle, or prime number, okay, prime circle will be a circle with a prime curvature. We'll also define twin primes, twin prime circles. Okay, so can anybody guess what twin should mean here? I'm not going to ask the curvature should be P and P plus 2. Okay. What should twin be here? So it should be tangent circles, a pair of tangent circles. So twin will be tangent, so pair of tangent prime circles. Okay. So in this picture, one, so for instance, 2, 2, 3. Yeah, so these are prime circles, and then this pair, 2 and 3, this is a twin prime, example of a twin prime, yeah? And Sarah showed in 2007 for given integral Apollonian packing, for any integral Apollonian packing, Apollonian circle packing, there exist infinitely many prime circles, as well as twin prime circles. Okay. But in fact, actually, to make this theorem true, in fact, I need to assume something about this integral Apollonian packing. I need to assume it's primitive. I mean, primitive means that the greatest common divisor of all the circles must be 1. Otherwise, we cannot hope for any primes, right? So, of course, we can rescale all the curvatures so that this will be primitive, and then we can talk about primes and twin primes. And you might wonder, why can't you ask maybe triple of prime curvatures, right? And by actually some parity argument from this quadratic equation, such a circle actually cannot exist. So there are no actually triple of prime circles. So you cannot go beyond the twin primes. And with the control bit to prove some final properties about these prime circles. Okay, so you know infinitely many prime circles and infinitely many twin prime circles. Is there upper bound for the number? Okay, or lower bound for the number? So theorem with the control bit. So we show that if you look at number of prime circles, so again, so P will be, so take any P which is primitive integral Apollonian packing, and so we know there are infinitely many prime circles. So look at the prime circle C in P of curvature less than T. So look at all the prime labelings which are less than T, and then we show that its number is bounded above by constant times T to the delta of log of T. So this notation means it's a less than some constant time to this for all T. Okay? And this is in fact the optimal bound. So it's in fact actually 3 order of magnitude. So since you know that when you look at all the integers which are less than T, you know that it behaves T to the delta by the previous theorem. And then when you go from integer to prime, actually you get this log of T like in prime numbers theorem. Okay? And the number of now twin prime circles, C1 and C2, pairs in P of both curvatures less than T, the T to the delta. And then when you go twin primes, you get square of log here. Okay. Okay. Yeah. So far we've looked at this Apollonian circle packing, and then we looked at this labelings of these circles by curvatures. But okay, so what is so special about this Apollonian packing? Okay, I mean, can you go beyond this Apollonian circle packing? So let's begin with arbitrary circle packing, and then let's see what we can say about this. Okay? So let's think about some circle packing in the plane. Let's see be arbitrary. So circle packing in C in the complex plane. So what do I mean by circle packing? So I just simply mean the union of circles which are disjoint but will allow tangency, okay, like in Apollonian packing. So they are disjoint except for tangent points, right? So we allow tangent points. So union of circles which are disjoint except for tangent points. Okay, so let's look at the maybe bunch of circles like this. Okay, and then we want to we want to label the circles by curvatures. Okay, and then we would like to ask if there is a similar asymptotic like this. And for this, we'll assume obvious things. So we'll assume this P is infinite. I mean, if there are only finitely many circles in P, then I know the asymptotic. So it's not interesting. And secondly, we want to assume the counting function makes sense. So in the sense that, so we assume P is something called the locally finite. And this locally finite would mean exactly our counting function makes sense. For any bounded region, E and say T, if you look at the circles in P of curvature less than T, but C intersect this E, then we want this number to be finite. Okay? I mean, otherwise, this counting function does not make sense. Okay? So what does that mean? So we don't want to have For instance, we don't want to have these circles which approach some given circle, right? Then there will be infinitely many circles of curvature similar to each other, and it will be infinite. So we don't want to allow such a thing. So, and we assume these two things. Okay, is this enough? And it's not. And the very important property about this circle packing, which enables us to count these circles, is that in this Apollonian packing, so how can you count the circles over here? In fact, it turns out it has a lot of hidden symmetries, which I'm going to explain later. And so we have to impose these conditions. So we have to impose this circle packing has a lot of symmetries. So I'll explain what I mean by symmetries, but for that, let me give some definition first. So consider some subgroup of Möbius transformations. Consider gamma, which is a subgroup of SL2C, and then let's say suppose gamma is finitely generated and discrete. Okay. So if you like a fancy word, then discrete subgroup of SL2C is called the Kleinian group. Okay. Suppose gamma is finitely generated discrete group, then a very important notion, a very important invariant of this gamma, which will appear in our theorem, is something called the limit set. The limit set of gamma, usually denoted by lambda of gamma. So this is obtained by this. We have here a complex plane. So we have here a complex plane. Take any point z in the complex plane, and SL2C acts on complex plane. Yeah, so it's gamma because it's subgroup. So you look at orbit of this z under gamma. Yeah, so this is z, maybe gamma 1z somewhere here, gamma 2z, and so on. Okay? You have countably many points. Okay, and then you take the accumulation points of this orbit. That will be the limit set of gamma. It's the set of all accumulation points of an orbit. Gamma of z for some complex number, and then it's not so hard to see that actually it does not depend on the choice of the base point. You can start from here or start from here, but the set of accumulation points where gamma accumulates, it will be the same. So this is something called the limit set of gamma. And then the second notion, which is something called the critical exponent of gamma, but instead of defining the critical exponent, let me just give you alternative definition, which will be the Hausdorff dimension of this limit set. Okay? So again, this limit set is a subset of a complex plane. It could be everything. It could be the whole complex plane. Okay? But most of the time, actually, it is, again, you get some fractal-like set, and then the Hausdorff dimension. So Hausdorff dimension of this limit set we will denote by delta of gamma. Okay, now I'm ready to state the theorem. About general packing. So we have a bunch of circles. And we assume that P has lots of symmetries in the sense that suppose P is for some finitely generated discrete subgroup gamma of SL2C. Suppose this circle packing is invariant under this gamma. It's invariant under gamma with finitely many orbits. With finitely many orbits. So meaning that, so we have here a bunch of circles, right? So now I have suppose I have some Möbius transformation. Then if I move this picture by a Möbius transformation, then I get again a bunch of circles because Möbius transformation preserves circles. But I want this packing to be invariant. So the circles, they can move with each other, but then this configuration should not change under this gamma. Okay? Okay? So and then such a gamma is called the symmetry group of this packing. And most of the time, if you take an arbitrary circle packing, then there won't be any symmetry. Yeah, why should we have some finite general discrete group which preserves this configuration? But let's assume that our packing has lots of symmetries like this. And then we also assume there are finitely many orbits, so this means that so we could start with only finitely many circles and then obtain the whole packing using these finitely many circles. Okay? So finitely many orbit means I start with maybe some finitely many circle, and then by applying gamma, I obtain more and more circles, and then this way we obtain whole packing. And we'll assume one more condition. Assume that this residual set of P is precisely the limit set of this gamma. Okay? So let me recall you that the residual set of P is simply the closure of all the circles in P. Okay? And then I've just defined the limit set of gamma. Yeah? It was accumulation points, the set of all accumulation points of an orbit of this gamma, and then suppose they coincide. It might look strange condition, but I'll show you lot of examples actually satisfy this assumption. Then we understand this asymptotic of the counting function. So then let me call this NT of P as before. Then again, there exists an explicit measure, Borel measure, omega, such that for any bounded region E in C, whose boundary is again an algebraic curve, this counting function NTPE is governed by this omega of E times t to the delta. Okay? Now this delta is the Hausdorff dimension of the limit set, which is exactly the same as the residual dimension of the packing, because my assumption is that the residual dimension is same as the limit set. Okay? So maybe I mean this theorem about all this Apollonian packing actually is a special case of this theorem. So to verify that, I'll show you what is my finite generated discrete group which preserves my Apollonian packing. Yeah? Okay, maybe let me draw this picture. So take any actually 4 mutually tangent circles in any given Apollonian packing, and then I look at the dual circles. So what do I mean by dual circles? So the dual circle is that, so between these 4 mutually tangent circles, there are 6 tangent points. 1, 2, 3, 4, 5, 6. Okay? And there are exactly 4 dual circles which passes through these 6 tangent points. So one is this one. The second one is this one. Third one is this one. And the first one maybe in this picture looks like a line. Okay? So here you have 4 dual circles. And this gamma, I take a gamma to be subgroup generated by reflections with respect to these 4 dual circles. Okay? So, or inversions. Okay? So let's call this 4 dual circle maybe by D1, D2, D3, and D4. Okay? And then this is generated by inversions with respect to DI. This certainly finitely generated is generated by 4 numbers. And inversions is not exactly element of SL2C because it will have determinant -1, but it's not such a critical point, and let me ignore this point. You can go to subgroup finite index that would put you SL2C. Okay? And let's observe that in fact this Apollonian packing is invariant under this gamma. Okay? So if I look at, for instance, this circle, if I look at, for instance, this circle, and if I invert this circle with respect to this yellow circle here, then I get exactly this one. Yeah, I mean, you need to think a little bit about actually what does inversion mean. I mean, one obvious thing is that inversion with respect to this yellow circle would put this larger circle into it, right? And then it has to, and then you do the preserve tangents condition. So actually it will be exactly this one, which is a part of Apollonian packing, because I didn't say, you should not think these 4 circles give you full Apollonian packing, and there are infinite circles. I'm hiding this. And then if I invert this circle with respect to this one, then where should I get it? If I invert this circle with respect to this yellow one, where should I get it? These two are yeah, it preserves this one. Right, exactly. Thanks. Right. So what it does is that this yellow circle fixes these 3 circles and then changes exactly the other circle into the other circle which are tangent to the 3 of them. And that's exactly what it does. Okay? And then other circle do the same thing. So inversion with respect to this circle fixes 3 circles and then reflects exactly 1 circle which are tangent to the 3 of them to another circle which are tangent to the 3 of given ones. Okay? So you see actually this inversions with respect to these 4 dual circles preserve the Apollonian packing. And so the theorem about Apollonian packing is actually a special case of this theorem. And in fact, you might ask, okay, I mean, are there real examples beyond Apollonian packing which satisfy these equations? I mean, which satisfy these assumptions in theorem? And finally, so I'll show you these pictures, and that will be end of my talk. And now I forgot actually how to turn on this. Isomorphic to the well-known Sierpinski curve. Okay? So you can also verify, I mean, you can also count the circles in this packing with respect to curvatures. This packing also satisfies my assumptions. And next, yeah, so this picture, yeah, so here, not everything is tangent to each other, but this one. So I didn't draw all these pictures. So there is this beautiful book by Mumford and Wright and series called Injurious Pairs, and then they have actually constructed a lot of limit sets for something called the Schottky groups. And these Schottky groups are some specific examples of, I mean, Schottky groups are some class of finite general discrete subgroups satisfying certain conditions. And then they actually, they illustrated a lot of limit sets, and then the limit sets are exactly consisting of these circles. So our theorem applies to all of these pictures. Okay. I guess that's it. Okay.
Thank you. Do you have more?